Welcome. In this video, we're going to talk about delta H and thinking of that as a ratio of kilojoules per mole reaction and think about what that means and how we can apply that in some problem solving. So remember, delta H, it's the difference in energy when you go from, you're comparing the reactants and the products, and delta H can be positive or negative depending on whether heat is being absorbed or released. In this example, we're seeing a picture of an exothermic reaction where heat is being released. So here's an example down here of an exothermic reaction. So let's take a look at this reaction in more detail and see what we can do with these numbers here. So we're seeing nitrogen gas and hydrogen gas react according to this equation. It's a combination reaction. And what we're seeing is that for every 1 mole of nitrogen gas, it reacts with 3 moles of hydrogen, and it forms 2 moles of ammonia, NH3. And we're familiar with stoichiometry doing calculations using these mole ratios and treating those as, ratios and saying, okay, for every 3 moles of H2, I'm going to make, 2 moles of NH3, or writing things out like ratios in that way. What we're doing now is we're adding in another value, and we're saying that when nitrogen and hydrogen react, they make ammonia, but they also make 92 kilojoules of energy. So it's like we're adding another stoichiometric ratio that we can use in a calculation. So we can say that for example, for every 1 mole of nitrogen that reacts, I'm going to make 92.2 kilojoules of energy. Or for every 3 moles of hydrogen that reacts, I'm going to make 92.2 kilojoules of energy. So it's another stoichiometric ratio we can use in a calculation. So if we see a question like this where I say, how much heat is released when 45.8 grams of hydrogen reacts? Well, just like in any stoich problem, my first step is going to be find mole. So I'm going to take this number, 45.8 grams of hydrogen gas, and I'm going to convert that from grams hydrogen to moles hydrogen. And I know that every 1 mole of hydrogen is 2.016 grams. However many sig figs you rounded that to is fine. And so when I do that, I'm going to end up with moles of hydrogen, but I want to find how much heat. So I want to find energy. So I'm going to look back here at my equation and look at my mole ratios, and I'll see, okay, it looks like for every 3 hydrogens, I make 92 kilojoules of heat energy. So that's the ratio I'm going to use here. For every 3 moles of hydrogen, I'm going to generate 92.2 kilojoules of energy. So when I go and plug this into my calculator, I should get negative 698. So that means that I'm going to produce 698 kilojoules of energy when 45.8 grams of hydrogen reacts. So again, you can think of delta H, this energy per mole. It's like another type of ratio that we can use in a stoichiometric calculation. Let's look at another example. So in this example, we were given mass and we try to figure out how much heat was being produced. Problem number 2, it's the opposite. So we have a chemical equation, we've got delta H here, but in this case, I'm given kilojoules and I'm trying to find mass. Still, a good first step in any problem solving is, I'm going to see if I can find mole. So I'm going to start with writing down the number that I am given, which is 267 kilojoules. Okay, that's how much heat energy I want to produce. I'm trying to figure out how much CH4 I need to burn to do that. Well, this right here, kilojoules per mole reaction, this tells us that for every 1, what we're seeing is for every 1 CH4, you react 2. It's going to react with 2 molecules of oxygen. It's going to produce 1 molecule of CO2, and it's going to produce 2 molecules of H2O. So what it looks like is for every 802 kilojoules are being released for every 1 mole of CH4 that is being used up. So I can stop and plug that in my calculator. Divided by 802 So that would tell me that I have 0.33, let's see, I should have 3 sig figs here. So I would need 0.333 moles of CH4 in order to make this much energy. I want to find grams though, so I want to keep going. So I'm going to do one more step and say 1 mole of CH4 weighs 16.0 grams. So I'm going to multiply that by 16, and I'm going to get 5.33 grams of methane gas. So that's one way you can set it up. I'm going to show you another way of thinking about it as well. So we can also think of it as saying, okay, I want to produce 267 kilojoules of energy. And I know that for every, that I have 802 kilojoules are produced for every 1 mole of reaction. And then I can say, okay, for every 1 mole of reaction, so every one of these involves 1 mole of CH4, and then 1 mole of CH4 is 16 grams. This is another way of kind of writing this out. And what I did here is I took this step right here and I broke it down into 2 parts. I said that this is telling me up here, this number is 802 kilojoules per every mole of reaction, and then 1 reaction involves 1 CH4. So you could do it either way. So you could say that there's 802 kilojoules per mole of CH4, or you could say there's 802 kilojoules per mole reaction, and then 1 mole reaction involves 1 mole of CH4. Those are 2 different ways of kind of thinking about this type of problem. Let's look at one more example here. This is, what makes this problem different is we have the same kind of setup. We got a reaction, we know the delta H of it, but this one gives us amounts for 2 reactants. This is we're reacting 136 grams of H2S and 288 grams of oxygen. So if we've got 2 amounts given, you always want to think, hey, this sounds like a job for limiting reactant. So step 1 is I have to figure out who is the limiting reactant in this problem. And the way I typically go about finding the limiting reactant is I pick a product, like let's pick water, for example, and I start with my reactant, like 136 grams of H2S, and I figure out how many moles of product would be made if all of my H2S reacts. So I have 136 grams of H2S. 1 mole of H2S is 34 grams. Often on the AP test nowadays, they'll give you the molar mass of the problem, so don't bother looking it up on the periodic table if they give it to you already. And then we know that for every 2 moles of H2S, we make 2 moles of water. I got this from our coefficients in our balanced chemical equation. So it looks like 136 divided by 34. It looks like we have enough H2S to make 4 moles of water. Okay, and then let's do the same thing but for oxygen. So we've got 288 grams of oxygen, and we can see that 1 mole of oxygen is 32 grams. And then based on our coefficients here, it looks like 3 for every 3 moles of oxygen, we make 2 moles of water. So if I plug this in my calculator, 288 divided by 32, that's 9 times 2/3, that's 6 moles of H2O. So what this tells me is that H2S must be my limiting reactant. And that's important to know because the H2S is the one that's going to get all used up in the reaction. In other words, once all my H2S gets used up, the reaction is going to stop because we'll run out of H2S. So if I want to figure out how much heat's going to be released, I should base my calculation on my grams of H2S because this is the one that's going to fully react. My oxygen will not all react. I'll end up with some excess oxygen left over at the end. So I'm going to take my limiting reactant. So I got 136 grams of H2S, and 1 mole of H2S is 34 grams. And then if I look at our balanced chemical equation, it looks like that 2 moles of H2S, each reaction, I'm going to go back and erase this. each reaction, which is this whole thing, involves 2 moles of H2S. So I'm going to say for 2 moles of H2S, there's 1 mole of reaction. And then for every 1 mole of reaction, I'm going to produce 1120 kilojoules of heat. So I'm going to plug this in my calculator, 136 divided by 34 divided by 2 times 1120. And I get, I think I did that wrong. I think I get 2240. Let me double check real quick. 136 divided by 34 divided by 2 times 1120. Yep, I get 2240. So that is how much energy is released here. So if we go back over and look at our different types, the key thing is that we recognize that delta H is a ratio. It tells us energy per mole, and we can use that ratio to figure out how much energy is produced when a certain amount of grams or moles reacts. We can use this ratio to figure out how many grams of something we need to get a certain energy. And then we also could do an limiting reactant scenario where you're given amounts of 2 different reactants, in which case first you have to figure out which one's limiting and then use that one to determine the amount of energy. Hope this helps. Thanks.